Hello, my name is Christian Geckler and I'm a PhD student at the Environmental Robotics Lab at ETH Zurich. Today I have the pleasure of talking about our work on a biodegradable origami gripper, actuated with a gelatin hydrogel for sensor attachment to tree branches. Forests cover over a third of all terrestrial land area, are home to a multitude of different species, and provide essential ecosystem services. Yet they are under threat. From deforestation, with 10 million hectares being cut down every year, and from the effects of a changing climate, such as increased extreme weather events like droughts and the spread of invasive pests. In order to understand the impacts of forests on biodiversity, climate regulation, and ecosystem functioning, as well as the effect of forest management strategies, we need to collect data at large temporal and spatial scales. However, the challenge is that forests are very difficult to access, towering dozens of meters above the ground and often situated in remote locations. Current sampling solutions such as climbers, canopy rafts, or cranes are expensive, cumbersome, and labor-intensive. These solutions simply do not scale to the dimensions needed to collect actionable sensor data from the world's forests. Microaerial vehicles present a natural step to introduce automation and scale sensor deployment. Several solutions to precisely place sensors exist, such as shooting sensors, placing sensors directly, or using a gripper, as in our previous work. Here we see the functioning principle behind the gripper. There is a flat, unfurled state where the cross-section resembles an upside-down V, and when pushed against the branch, it flattens and transitions to the second coiled state. The coiling force is given by an elastic band seen in green. The gripper and sensor can then be deployed on tree branches using a microaerial vehicle. However, none of these solutions adequately address the issue of sensor recollection, either neglecting it or requiring complex maneuvers. Nonetheless, recollection is essential to avoid electronic waste and the release of potentially harmful substances into the environment. Ideally, fully biodegradable sensors solve this problem, as they can decompose into harmless substances at the end of their useful life cycle. Much promising work has been done, such as biodegradable antennas, batteries, actuators, and even full sensors. However, such approaches are still under active development and not viable to be deployed in the field. In contrast, a feasible alternative is a partially biodegradable hybrid approach, which contain biodegradable components, such as structural or attachment mechanisms, but conventional sensing, communication, and battery elements, since these are the most difficult to replicate with biodegradable materials. This is the approach we follow in this work to develop a biodegradable origami gripper to attach non-biodegradable sensors to tree branches. Origami manufacturing consists of a laminate of rigid and flexible layers, with an engraved pattern in the rigid layers enabling folding. For biodegradable origami, a suitable alternative for all these layers must be found. For the rigid layer, we chose balsa wood due to its lightweight and high strength-to-weight ratio. For the flexible layer, linen cloth was chosen since it has a high mechanical strength and is suited for repeated folding. As an adhesive, a dextrin-based starch adhesive was used since it is widely available and well studied. Lastly, gelatin hydrogels present high elasticity, fast biodegradation, and simple manufacturing, and were thus chosen as the actuating elastomer. The hydrogel dissolves in the presence of moisture, releasing the gripper from the branch and facilitating easy collection of the electronics from the ground. The two main properties of interest for the gripper are the maximum holding force and its degradation with moisture. The maximum holding force is directly determined by the properties of the gelatin hydrogel. The ultimate tensile stress before break of the hydrogel is around 0.9 megapascals at a strain of 3.5. To see how the gripper performs under a sustained load over time, we measure the creep by placing a sustained constant stress over 6 days. After the first hour, the creep plateaus, reaching the maximum of 55% after the full 6 days. The final gripping force of the full gripper is around 1 Newton. When exposed to sufficient moisture, the gelatin degrades and the gripper falls, a really easy collection of the electronic components from the forest floor. Finally, to demonstrate the applicability of the biodegradable gripper to deploy sensors, we attach it to a branch with a micro-aerial vehicle. In summary, we substitute biodegradable materials to develop biodegradable origami. This is used to replicate an origami gripper for sensor attachment to tree branches. A gelatin-based hydrogel is the actuating elastomer, which degrades once exposed to sufficient moisture. This drops the biodegradable gripper, allowing easy recollection of the non-biodegradable electronics. In the future, we will look at tuning the water resistance of the hydrogel and the effect of outdoor conditions, such as microbes and temperature, on degradation. Overall, this is a first step towards scalable and more environmentally sustainable ecosystem monitoring. Thank you.